Hi. Is the screen visible?
Yes, your screen is visible, but there is a great noise in the background.
Oh, it may be due to fan, I guess. I think I can't do anything about it. Is it a more amplified noise or just tolerable? Hello?
I'm hardly hearing your voice. That's why I'm not able to answer your question. Your question is a little bit superimposed with some noises.
Hello? Is it fine now?
Yes, your voice now is very good.
Okay, thanks.
Yes, thank you so much.
The session starts after 6 p.m., so we can wait for 5 minutes, I guess. So maybe others will also join. Till then, you can tell me, did you guys had any other session yesterday or day before yesterday? If anyone else has already joined the session, because this session will be more of same repetition of that. I guess till then, I will give a brief introduction about me. My name is Mohammed Sajan Nazi, and I'm a PhD student at IIT Kanpur. This session is a part of PMRF teaching duty. PMRF is one of the scheme that funds the PhD student, and as part of it, we have to deliver a 2 hour session or lesser per week. So, in addition to the course, you may have other TAs as well. This is a additional sessions and other TAs that are responsible for the questions and everything assignments that are different than us. So, one may have already given the session, and this is the second session for the same week. If you have any doubts or any questions related to the sessions, you can please turn on your mic and we can easily talk for 3 4 minutes.
Are we going to have some practicing and solve some problems in this session?
This session, again, as I said, we are giving a set of questions. We have to show that set of questions to you, and that may be similar to the ones which you have to do the assignments. Like you have assignments for the sessions, it will be almost the same as those questions. And these are the allotted questions. We have to show those sessions only. Yeah,
Okay.
it is somewhat a practicing session.
Mm-hmm, mm-hmm.
Where people are joining, we can wait. Yeah, this will be the link and the video recording. Everything will be shared by the NPTEL team. So, are everyone here undergraduate students? Because this is a undergraduate course, I guess. Yeah, please. You raise the hand. You can unmute yourself. Cover. You can say if you want to say anything.
Nothing, sir, nothing.
Okay, okay.
That good evening.
Good evening.
Good evening, sir.
So have you gone through the lectures of this week?
This week's 1 hour I have completed. Rest 2 hours I have to watch. Like I had internals, and I
Okay,
have now.
okay.
I have to keep it. I'm attending this session just to screen record so that
Oh
I can
no,
follow it later.
you will get the recording. You don't need to record.
Okay, I wasn't knowing this about this.
There is
Now
a
you can get the.
uh, one at a time, please.
That's why I'm here today.
Uh,
I have interns. I'm preparing for it
okay,
just to
so there was a
keep it
session
in
also yesterday. Did you attend that session?
yesterday. No, no, I did the same. Like I log in at 6:30, I guess. From
Okay.
then I kept it for screen recording. I
No,
have to watch it.
you don't need to do that. You will get the recordings and PPTs and everything from the NPTEL team. So
I
you don't
haven't
need to.
received those yet, so I thought,
Mhm. They will
uh,
share. They will share. Don't worry about it.
okay, sir, thank you.
Maybe they will. They want you to first submit the assignments, I guess,
Yeah,
because there will
by
be.
Wednesday at 11:59,
Mm, mhm.
the first assignment.
And I guess the questions I have kept in this presentation are more or I guess same the assignments you have been given and you have to
Okay,
do. So I will do the questions, but I won't give the final answers in the session because it will be as if I'm doing your assignments. So first, I will give a brief introduction to the basics of. We have started with the diode. First, I will give a brief introduction to the diode. Then we will start the question set. Fine. So
yeah, yeah.
if we can
So
start, right? And I
just
guess,
one doubt, just
yeah,
one doubt.
mhm.
Presently, now I am in second sem of
BTech.
ECE.
Okay.
Is it proper of choosing this course? Like digital electronics, I went through the course outcomes.
Mhm.
It is just the same as what I'm studying now.
Mhm.
That's why I chose this.
For the
I
first,
know this is tough for my level.
mhm. So let
Is
me
it
tell you, the second sim, this is a very basic course, as far I know. Analog is a basic analog course. So
okay?
it will help you. No matter if you don't understand the whole course, don't worry about it. So if you even get the 50% or 30-40% of the course, it will benefit you very well. So you don't need to worry about it. You will understand if you properly follow the lectures. You will
Okay,
slowly understand the topics.
okay, sir.
And
Thank you.
if you any have doubts about it, about the lecture weeks, we have 2 sessions per week. You can anytime join the sessions and ask the doubts.
Yes, sir. Sure.
Okay. Let's wait 1 or 2 minutes. I guess we can start. People will be joining. So these are the basics regarding the sessions that you, basic rules that you have. Everybody is mature enough to know. So we can directly just. So week 1 was mostly about the diodes. So you may have seen the assignments. Is the screen visible and am I audible properly?
Yes, sir.
Okay. So, does everyone know about the diodes, this working? Because you may have seen the lectures, the professor directly goes to the circuit point of view. So, do you guys have the idea about the basics of the diode? How diode is made, how it functions. Okay, so
Yes, yes, sir.
first let's start with semiconductors. So, we are dealing with the analog electronics, so we need to know a basics related a slight idea about the semiconductors. Anyone, what is the semiconductor?
It's a material that has a conductivity level in between the two extremes, insulators and conductors.
Okay, conductivity in between conductors and insulators, right? Okay. So, and another thing is we can control we can control the current flowing through the material, right? Let's see a bit about it. So we have semiconductors, we have intrinsic, and another is extrinsic.
Extrinsic.
Extrinsic, right? So, what is an intrinsic semiconductor? Anyone?
A pure kind of semiconductor. No impurity atoms are doped inside this type.
Okay. And from the concentration point of view, you can say that number of holes and number of electrons are equal, right? So you know the notation. You have an intrinsic semiconductor, let's say of silicon, right? So it will have only silicon atoms, and if you by any means you can see the number of, let's say, electrons to be 10 raised power 22 per cubic centimeter, and you will see that holes will also be equivalent to 10 raised power 22 per centimeter cube. This is a notation for this how you define the concentration. But another type is extrinsic, which is used to make a PN junction. What is an extrinsic semiconductor? What are the types of extrinsic semiconductors?
P type, N type.
P and N type.
Okay, 1 second, I will admit people are joining. So what is a P-type semiconductor? Which carriers will be in majority?
Holes.
Okay, nice. Holes will be in majority, right? And another one is
Electrons. N type.
N-type semiconductor. So electrons will be in majority. So you may have seen P-type semiconductor is made using the doping of third group elements, right? You have seen the chemistry you may have studied during your 11th, 12th. In the periodic table, the third group elements, boron, aluminum, gallium, and etc. These are used to do P-type doping. And for N-type doping, which group we use?
Pentavalent.
Okay, nice. These are used for, this is a fifth group, right? Phosphorus, sulfur. So this is the type of doping we do. We introduce an impurity in the intrinsic semiconductor. So to increase a particular concentration, let's say for in p-type we have holes and in n-type we have electrons. So do you know basics about the band diagrams? How does p and n-type and intrinsic semiconductors look?
Yes.
Okay, so I will draw a band diagram of a semiconductor. Let me know what it is. uh, this is EV. What does EV represent and what does EC represent?
Valence band and conduction.
Okay, and what I have just drawn, what is this EI?
Fermi energy level.
This is the intrinsic Fermi energy level, right?
Yeah.
So what if I draw EF? EF is also here. That is a Fermi energy, and EI is the intrinsic level. Which type of semiconductor is this?
Intrinsic
In
semiconductor.
This is an intrinsic semiconductor, right? 1 second. So this is an intrinsic semiconductor. Intrinsic SC. Now, if I want to draw a band diagram for If I now want to draw a band diagram for P-type semiconductor, can you help me with it?
The Fermi level, I think, will bend a little bit downward.
Okay. Fermi level will be closer to EV or closer to EC. In
EV.
one second, let me admit the students. So it will be closer to EV, right? And similarly, if you see N-type semiconductor, you will see a Fermi level closer to EC. Now, in PN junction, what in the name itself, one second. So, PN junction, a junction, you know, what is a junction? You join the two materials, materials with different properties. You join them, you make a junction, right? So now, in PN junction, you have P type and you have N type. Now you know P and N are the extrinsic semiconductors. So what will happen? Here are the majority of electrons and here majority of holes, right? If I connect the wires here, so what will happen?
Diffusion current.
Okay, why will the diffusion occur? And from wire to
Due
wire?
to concentration gradient. Concentration gradient.
Okay, so there is a concentration gradient for electrons in this direction and for holes in this direction, right? So what will happen is electrons from N-type semiconductor will try to move to the P-type. And here, as I said, if you have pentavalent doping, let's say we denote it by Nd, it had 5 electrons. Now it has lost 1 electron. So what will remain here? 4 electrons. Because if you want to replace a silicon, silicon is a 4 electron atom, right? It has a 4 valence electrons. Now it got replaced by, let's say, phosphorus. Now it has one additional electron. Now if it loses this electron, what will be the valency of this atom? It will have a positive charge, right? So if from n-type p-n junction it loses 1 electron to here, so there will be a positive charge development here. Do you understand this point? Similarly, there won't be a single atom. There will be multiple atoms that will lose the electron and that will go to the p side. So here will be a layer of positive depleted charges. Similarly, from the p side, you have acceptor atoms. Let's say this was a silicon, it got replaced by aluminum that has only 3 valence electrons. So now it has this position, it can receive 1 electron, right? So now if it receives 1 electron, it will obtain a negative charge. So that's what happens here, development of negative charge. So what is this region called as? So this formation of region.
Depletion region.
For 9, this is a depletion region. And can you tell me the potential, what is the electric field direction in this region? Can you tell me the electric field direction in this region?
Toward the P side.
Nice. This is a electric field direction. So have you heard about built-in potential in the PN junctions? So
Yes.
this is what actually the built-in potential gets developed. This is how actually the built-in potential gets developed. This is the electric field direction, and after this potential development, the current will stop to flow. If electrons were flowing in this direction, the current will be in this direction. For till you have a built-in potential that we denote by VBR. So that is a built-in potential for this PN junction. Now, from the band diagram point of view, how will it appear? This was a P type, this is an N type, and let me just draw a junction. If I connect them two, so how will it appear? Ever done this? So this is a Fermi level of p side, this is a Fermi level of n side. What happens is if these electrons go on this side towards this Fermi level, the concentration will reduce here, so this Fermi level will go down, right? And if concentration increases here, this Fermi level will go up. This is I'm saying in the layman terms. So what happens is you get a band diagram, and we get a constant Fermi level. This is your built-in potential if you want to visualize it. This is a EC, this is a EV. So now during your forward bias, now you have all have heard about the forward biasing of your PN junction, right? What happens in forward bias? One second. So as I said, what happens in forward bias is this was your band diagram. This was your built-in potential. What happens is you have electrons here, they have to travel here, right? So when there is no external supply applied, these electrons don't find enough energy to go to the p side. So what happens is if you apply voltage, that gets subtracted here, and that reduces this barrier. You can see this barrier that gets reduced. Let's say I will just say this got reduced in this way. So more and more electrons will now be able to go here. This is how a basic PN junction operates. But if you do a reverse bias, this will potential will further increase. VBI plus V. That won't help electrons to travel to P side. Similarly, from depletion region point of view, you know if this is your under zero bias condition, if you apply a forward bias, you get a shrink depletion region, right? You get lesser number of carriers here. That is because this band bending. Okay, so I guess this is enough for the PN junction basics. Now we can say that directly in forward bias we have enough conduction. In ideal case, let's say in ideal case, we can say that diode is short circuited, and non-ideal case, we may have some resistance in series. Because you know, any material, when you pass the current through it, except it's a superconducting material, it has a resistance, right? So, shall we start with the question? Do you have any questions till now? Anything related to PN junctions? Hello? Anyone can confirm? Can we move?
Yes, sir.
Yes,
So,
sir.
I guess this is the same question you have been given assignment.
Yes.
Mhm. Okay, so let me just first try to understand. Do you have a clear understanding of a PN junction? Can you please tell me if I draw a circuit in this way? V in is simply a voltage. You increase it from minus 5 volt to 5 volt. So can you tell me what will be a plot between, one second. V output and V input. Assume that you may have come across the many different diode current curves, right? You have seen this curve, right? IT versus V. This is your cut-in voltage. And here I will tell you to assume that this is a perfect ideal. This is a perfect ideal diode. You have this ideal. This is V. This is your negative axis. So can you tell me what will be V output by V input? How it will appear? So V input will increase in this way from minus 5 volt to 5 volt. Can you help me out with
Yes,
this?
I think
So
so. Yes.
yeah. So this is a V input. This is a V input function. So if I say V input is 0 volt, so V output will also be 0 volt. Does because both diodes will be off, right? So now if I increase V input, which let's say I will assume this as D1, I will note it as D2. So for positive biases, when V input is positive, which diode will conduct?
D1.
D1 because this is
D1,
forward bias.
D1.
Forward bias.
Okay, so D1 conducts. And if V goes from 0 to minus 5,
Then D2 conductor.
D2.
yes, because
G2.
this is a N
Positive.
side, this is P side, it will go forward biased. So it will simply follow your V input. Simply Y is equal to X, right? So, okay, so now you have the diode understanding of how it appears in forward bias, how it appears in reverse bias. In most of the cases, you will see that we need to apply either this model or we need to apply this model, where we say that this is a cut-in voltage. Most of the questions it will be given, and somewhere we will have to assume, right? So, have you tried this question? Let me just first ask you guys. This was in the assignment. Did you find the right answer? Okay. So, what does the question say? You have diode and resistor in series. Okay, let me just write a point. Point note. Whenever, whenever two components are in series, just remember this. Current will be same. Is it right? So if you have
Yes.
here, if you
Yes,
have
sir.
your diode and resistor in series, you cannot have diode with one current and resistor with other current. So that will violate the law of charge conservation, right? Because you cannot just produce the charge randomly in a circuit. So whatever charge comes in has to leave out. So if we are advised in this question to use, we have to find a current ID and give your answer in milliamperes. Solve the problem iteratively. So why do we need to solve this problem iteratively? We will see because for the diode we have IS exponential of V that is applied across the diode by Vt minus 1. This is a basic diode equation, right? And
Yes.
another thing is if you see across the resistor, so if it has a potential of Vd here, you can see. So what will be the potential across resistor? Simple KVL. Apply KVL from top to bottom. Do you know about the KVL?
Yes, V output minus VD.
Okay, so you will start from the output. You start from the output, then you subtract. What is the drop? Drop is your VD, right? Then you see what is the further drop here. That is ID multiplied by R. ID multiplied by R, and it will be equivalent to 0 because here it is a 0. This is ground here, right? So this is how we apply the KVL. So you have one more definition for ID here. That will be V naught minus VD by R. Now you see here, you have two equations, right? So now you will get confused of which equation you will use to get a value for your question here because we need to find ID. So what you do in this problem is that you do a numerical solution. First you guess value. I won't say I just directly I guess a good value. Why I'm saying good? Because then only you will converge to a better solution quickly. Good value for a variable. Here we will directly guess the value of PD, right? And another thing people will do while doing the questions of this type is that they use this function. This is, let's say this, I assume this as A. They use this function directly. Just know that whenever you do numerical solution means you find a value of some variable in this equation, let's say in B, you substitute that equation in A, then you get a value in A, then substitute back in B, and you do this iteratively. This is how you do the numerical solution. But know that in numerical solutions, always try to use the functions which mm, converge at large values, which converge. Let me just make myself clear. For example, you see exponential of x. What is the graph for exponential of x? Yeah, right, like this way, right?
Yes.
So if you see, if by chance while doing a numerical solution, your VD your VD gives a value that gives a very, because this is an exponential function, right? That gives a very high value of ID. You will never be able to get a converged solution for your question. So because you can see for every value, increased value, your ID will always increase because of this exponential function. So what illustrated people do is that they use a logarithm function. Here you can see this solution doesn't exceed. One second. So always try to use the functions which converge at large values. So what we will do is that we assume this diode equation we have already assumed. So what we'll do, we assume exponential term is greater than 1. So it will be Vt.
May I ask a question, sir?
Yeah, please.
I just want to know particularly what is meant by it converge at large. What is meant by converge?
Okay, so let's say uh, this is id equal to e raised for x, and then you have another function like in this way, id is equal to v naught minus vx, sorry, this is x, let's say, by some value r. So you give this x value a one value, right? So do you have you ever tried numerical solutions? So you will understand that if you get a value for x here, let's say 1.2, you obtain a value of id, or vice versa, you have a value of id, you obtain a value of x, right? Then you substitute this value of x here, right? So you get a new value. Let's say new value is x plus delta x for x.
Mm-hmm, mm-hmm.
So you get a id of e raised power x plus delta x, right? That is your initial value, your new value. What will happen is that if you use the exponential function, it will give a very large value of your id, because in numerical solution always see that you use an error between your initial guess and your obtained value. So what can happen is that this value can increase, your delta can increase, and in numerical methods, if you have MATLAB, or you can use online platforms to solve the numerical solutions, you will see that if this delta increases, your answers will never converge. Converge means to reach a particular value. For example, if I had guessed, let's say 0.65, and built-in potential for diode and is let's say for silicon is zero point 0.7, so it should be less than zero point 0.7, so it should never exceed this value. But if you use the exponential functions kind of functions, this value may go above this zero point 0.7 value, or maybe go hundreds, thousands. So that means it didn't convert. So converge means to go to a particular near about your guess, I guess, say. So it shouldn't go, it shouldn't deviate much from your initial guess. I hope it's a little bit clear. You can use the simulation platforms to, or you know how the Newton-Raphson methods. These are some methods, or you may have studied the graphical methods as well. So these are few methods why you need to lower this error term to get an answer that is very close to the one you are looking for. One second. Okay, so what we'll try to do is that we will change this function a into logarithmic one. So what we will get is that we will get vt ln of id by is. Okay, so other function we have is id equivalent to v naught minus vd by r. We obtained this equation from KVL, and this is from diode equation. Okay, one second. I don't have this. So can you tell me you have, I guess you must have tried these assignments. So how did you start with these questions? So the question clearly says that you have to do iteration method. So you may have seen most assumed value for VD in this question set is 0.65 volt, right? This is this voltage. This is your IDVD, and if you extrapolate it here, this is this voltage, right? If I just assume it in this equation, V naught is given us to be equivalent to
2.58.
2.58. Thank you. So my ID will be 2.58 minus 0.65 divided by what is the value of R? 0.09 kilo. 1 second, 7. So So this is a how you will find the ID. Let me just write it here. So my ID will be. Can anyone tell me the value? Find it.
2.14.
2
144.
milliampere, right? Because it is K. K stands for K. So we get a value of ID as 2.14 for milliampere. What will be the next step? Can you tell me the next step?
Put the value of ID in VD.
hmm So next step is we substitute this value in equation. Let's say this is A, this is
1.
B,
A.
equation A.
Question.
Okay, so my
For
equation,
VD,
yeah,
plugging in for VD.
yes, yes. So this will be 2.144 milliampere by IS.
Upon.
IS
Yeah,
is given to you. IS is given to you, right?
absolutely. Given. It's given.
Okay. So what is IS actually? I forgot to ask you guys. What is IS?
Uh,
Saturation current.
Reverse saturation current, diode reverse
Uh,
saturation current.
Why is it called as
1.
reverse saturation current?
Minority
Anyone?
current.
I mean to say, why is it called as saturation current, reverse saturation current?
Reverse saturation current.
So this is this equation, this current, right?
Sir. Yes,
Hmm.
sir.
Okay. It has nothing just physical significance. It is because if you see the diode equation,
Hmm.
IS, it's seen that if you plug in the value that is minus by Vt minus 1, this term goes to 0, ID is Is. It is seen that the value of Is is closely related to reverse bias current. So, and we call this as reverse bias saturation current. So that is the name for this IS. If you do you won't study that now. When you do the higher studies, you will see how this IS appears. So it's just a name. It has no physical significance as such. It's because in reverse current, these magnitudes are almost same. So that's how the name has been given to it. So can you do this after this? After you find the VD value, let me just do the first iteration, then you can do the rest iterations. So you help me with this. This is VT. VT is given to us as 26 millivolt, right? That is 26 milli. And just don't do this wrongly because this is ln, and another is log. You will use the calculators to solve the questions. In ln, you have to use to the base e,
Absolutely. ln. Absolutely.
to the base e.
Cancelling the exponential, we'll have
Yeah,
ln.
because in calculators you will see there is log as well, that is to the base 10. So
Hmm.
people may get wrong
Hmm.
answers.
No, no,
So
no.
you
It
know,
should be ln.
yeah, it is ln, right? That is a
It
natural
should be.
logarithm.
Yeah.
So this
Yeah.
is 2.144 into 10 is power. After plugging the is is of the order of 10 is power minus 16. You,
1.6 into 10 to 1.
you will get 10 is power minus, you get 10 is power 13 here. Here, and this was 1.9, right? So you can do this. This is first iteration. I will just, you can just skip it in two parts. You can do this in two parts. Ln of 2.144 by 1.9 plus 26 milli ln of 10 is power 13 to make it easier for you guys. So you can do in this way as well. Can you tell me the value of first iteration? Can you use the calculators for it? I will also use my calculator. What is 0.6? What is the first term? Just correct me if I'm wrong. This is 0.314 plus this will be 26. This is directly 26 milli into 13, right? Into but you will have a value for ln as well, ln of 10. So it will give me ln of 10 into. So is it correct here? Did you get the same value?
Yes, sir.
Yes, sir.
Okay, so this is. So can you see the difference in your first guess? First guess was VD equivalent to 0.65. So what did we get? 0.7814. So if you see the delta here, the VD has increased. To the guy who first asked me the convergence, what if in second iteration, this value, this final value further increases? If it increases, that means your solution your solution is not converging. If you use a simulator, you will never get a solution, right?
Sir,
That will get
sir,
stuck in an infinite loop.
10,
Yes.
सर वैल्यू ऑफ आई एस 10 रेज टू पावर 16 होगा ना वो जो
Yes, here, listen here. So it is okay, let me just write it. 26 milli ln of 2.144 milliampere divided by 1.9 into 10 raised power minus 16. Is it what you are talking about? So यहाँ पे milli, this is milli is 10 raised power minus 3, right? So
क्लियर
can I here
Yes.
this is 10 raised power minus 3. So if I do this in the denominator, it will be 10 raised power 13. Okay. So what we got in the first iteration was now VD equivalent to 0.7814. We substitute again in equation B, sorry. Now equation B is ID V naught minus VD by R. Again you will find value of ID, then again substitute in A, you will find the value of VD, right? So you have to do this because I won't do the final answer because it's, I guess, the same as your assignment you have to submit. So is this question clear how it has to be done? If you have any questions related to this question, you can just ask. Let me just see the, okay, 1 second. The options for this, you need to do iterations till you get an answer close to your options.
So when will we stop? We are going to go through a number of iterations. So when will we stop these iterations?
Okay, so the thing is, if you use this software, you can use a condition for it. Most of the softwares, what most of the softwares use, because in iteration method, we should stop. We fix the error. Fix the error. Please tell me if you will understand this. We say that if error, let's say delta, is less than, let's say 10 is power minus 6, then stop. Okay. So this is how we impose the condition, if you want a very further good answer, you will say, let's say, if the error is less than 10 is for minus 9, 10 is for minus 10, between the two solutions. You got the first solution, your guess was 0.65, and you got VD1 as 0.7814, right? So you subtract the two, there is a very lot of difference there's a lot of difference in the two values. So you again do the iteration till your delta is almost, you can see if it assumes now the constant value, let's say it goes fixed at zero point 0.6. Now if you do another iteration, it gives you a value of 0.60001. The next iteration it goes to 0.00001, let's say 1.1. So you say that if you need your precision up to 2 digits or 3 digits, you can say that I can stop here, right? So it's up to you.
Yes.
So you in this iteration type of questions in which you have to do by hand, try to get the answer which is near to your solutions, and that will do. But in simulators, you can set the simulators at thousands of iterations to get a very correct value. So try
Mm-hmm.
do one thing. Do one thing. Everyone has an internet access. You can use Google how to use numerical solutions, how to do numerical solution online. You can use MATLAB. MATLAB can give you the way how you can try it online, right, as well. But for these questions, you can get your answer in 3 to 4 iterations, or in fact in 3 iterations. So you don't need to go beyond 3 iterations, right?
Mm-hmm. Mm-hmm. Okay.
So, any other question for this? And another method for use doing the questions is maybe you may have also gone through the lectures and you may have studied. That is a more easy way, but you don't have to do that in this
Hello.
question. So let me just do a graphical method, right? We have another method that is a graphical method. Everyone has an Excel. You can plot this in Excel as well. You can plot in any tool which you are familiar with. You see that your ID is is exponential of VD by VT minus 1.
Hello.
Hi. Hi, Krishna.
Hello.
Hi, Krishna. Yeah.
Can you explain the iteration method once?
Okay, the previous one.
Yes.
Okay,
One
so,
iteration.
hmm?
One iteration.
Okay, first iteration. What we did is that first we used this equation B. We assumed the value of VD to be 0.65. Okay, we got the value of ID here.
Okay.
Then we substitute this value in A. Equation A is here, this equation. We substitute this value ID in this equation.
Okay.
One second, clarify. Then we obtain another value of VD using this equation that is equivalent to 0.7814. Now you can see your assumed value and this value, obtained value VD1 is very distant, right? So what you do is that you assume again this 0.7814 in equation A. You again will calculate the value for your ID, right? This equation, and again you will do this kind of stuff 2 or 3 times till you get an answer, which will remain nearly constant, right? Then it won't like here you can see VD is 0.65, another is 0.67814. It is a very distinct, it's very naked to the eye, right? So values are really different. But once you do 2, 3, or 4 iterations, you will see that your values will start achieving a constant values, right? So this is your assignment. You can do it and then try to do 3 to 4 iterations. So I think you should get the answer.
Thank you.
Okay. So another method, as I said, is a graphical method. You can use a tool to do this. Okay. So let me just draw.
I think the solution will be the intersection point.
Yes, yes, yes. So this is your ID. This is your VD. So what will be the graph for this equation? Question B. We call this load line. So when VD is zero, your ID is max, right? When VD is equivalent to V naught, your ID is zero, right? VD is equivalent to V naught. So you have to just join these 2 points. So you get this. And for diode, you have this equation, right? So this will be your ID operating, right? So this is one way to solve this question as well. But you don't have to do this. You have to do numerical analysis. Okay. You cannot do this by hand. You need exact scales, x-axis, y-axis to get the proper values. Okay, moving to the another question.
I want to ask a question, please, before
Yeah, yeah.
moving forward. You have said that the negative slope straight line that you have drawn for ID and VD,
Mhm.
you have said that this is called the load line. Why it's called the load line?
Okay, in DC analysis, you will see any load. This R is actually a load. Load is where you take the output from, and name actually is from that. You have any V input, you have RL here, V output. So this is your load. So this line, this DC analysis that comes from the listener is called as a load line. This is just a, this gives you a points of the operating points which which will be available, or which can, for example, which is a combination of your I naught and V naught here flowing through this. For example, this is a resistor. So here R is our output resistor. So this is in DC operating analysis, we call this as a load line. And similarly, if we are doing AC analysis, and then if we see how your I output and V output varies with the resistance, that is called as the AC load line. Okay. So this is a very similar question to the previous one. You have to just find the ID. So what is it? The output is 2.5 volts. The resistor R is similarly 2.9 kilo ohm. Assume a cut-in voltage of, as I said, most of the questions, it's assumed that it's equivalent to 0.65. So we can directly, from the options, you will see that if you directly use this, cut-in voltage is given as 0.65. You don't need to do a iteration because it's itself saying VD is 0.65. So we need use of 0.65. Can you do it? Is this correct? What I have accepted? Because
Yes.
if you do a KVL from top to bottom, it's V naught, then there's a drop of VD, then there's a drop of ID into R, and that will be equivalent to, this is ground. Ground is not, we can note the ground as GND as well. So this is simply 2.58 minus 0.65 divided by R is 0.9 kilo. That was just calculated in previous question as 2.144
2 point.
milliampere, right? Is it right?
Yes, sir.
Just
So
Yes, sir.
one more thing in this question is that we are assuming a diode without any resistance. But if you see that diode also imposes a resistance denoted as RD. Now we will see in further questions we need to use this RD. Yeah, please. Someone was asking something. Hello.
yes, we can hear you very well.
Okay, so you were asking something?
Yes, I want to ask when the question involves this assumption that assume a cut-in voltage is of
Mhm.
0.65 volt, we are not
Mhm.
going to go through an iteration. I
No, no,
understand this.
You don't need to
Okay,
go. Okay.
but my question is, if I take this VDE and substitute it in the exponential equation, I am going to get the same ID that I have got from KVL.
You mean to say if you assume it in this equation,
Yes, yes.
okay,
And I
so
substitute V to 0.65.
this equation won't necessarily give you the exact same equation because this is an approximated relation as well. But mm, what you can do is because there is other factors like ideality factor is there. You don't know is accurately here, right? So you can try. You should because for ID should be equivalent to IR. That is a given thing because there will be a also we are here neglecting the RD as well because in diodes, there will be a series resistance that will also restrict your current. You can just you can substitute the value of VD in this equation. You can check because ID should be similar to your IR. You can just put the values and you can calculate it because these elements are connected in series. They should get the same value.
Mm-hmm, mm-hmm. Yes.
Okay.
Okay, thank you.
Okay. Okay. So okay. So now, can you see the question here? You must have tried it. Anyone can say anything about this question? Uh, you have gone through the assignments, right? Okay, so let me just get an idea from you guys. What if I have, what will be the potential across this resistor?
5 volt
5 volt. Why? Because they are in parallel
parallel.
combination. Okay, so here the question says, one second. Okay, 5 volt, yes, parallel. So in the circuit below, the diode has a cut-in voltage of zero point 0.7 volt. Just have seen one thing from your diode characteristics that it is actually a very sharply increasing. So your diode cut-in voltage, you see that even if you increase the applied voltage, actually this should be applied voltage. Even if you increase the applied voltage, see, even if you increase the diode voltage here, this is VD, right? Even if you go on increasing this voltage, this VD here, you don't see a current in this region. So what happens is actually from the band diagram point of view, you saw that this is how you see a bending in this. So max what can happen is they will just go parallel. So that is equivalent to built-in potential, right? So that is what for the silicon we have is zero point 0.7 volt. So it cannot grow beyond zero point 0.7 volt. So maximum potential drop across the diode is zero point 0.7 volt. If you go on increasing the external bias, that will just damage your diode. So we can say that this diode can act as a simple potential here, potential drop of 0.7 volt in parallel to a resistance that is here R1, and this is your Vx and this is your R2. This is a case when we assume it is in on state. So do the analysis. If you do the analysis, we need to find Vx is given as 6 volt and these are the resistance values. What is the current for R2? So you don't know at first if the diode is in on state or the diode is in off state. So what will it do? We'll start with the assumption, right? Assumptions. There are two assumptions here. One, diode is on. Diode is only on when we applied. That is here Vx is above V cut in, right? And another assumption will be diode is off. So let's say when diode is on, it will give me opposing voltage of 0.7 volts. This is R1, this is R2. Can anyone help me with the analysis? So we need to find this current. Let's say this is I here flowing, this is I diode, this is I1. So what will we do? Can anyone tell me what will be the nodal analysis at point A? Remember that whenever you have to find the currents, you try to follow the KCL, Kirchhoff's current voltage law, right? Can you tell me what will be the KCL here? If the current is flowing here in this direction,
Vx minus Va equal 0.7.
Vx minus,
Va or Vr.
so I mean to say KCL. For example, here this is I2, this is I1, this is ID. So ID plus I1 will be equivalent to
Equals to
I2,
IL.
right? This
Yes.
is this correct?
Yes, sir.
Okay. So just so now, what is the potential difference between this node and this node? Here you clearly said in parallel the potential difference is 5 volt. So what will be the potential difference from this node to this node? This node and this node. X node and A node.
0.7.
0.7, right? So it will be simply ID plus 0.7 divided by R1, and what will be the I2? Vx minus 0.7. Please stop me if it's not clear. Divided by R2, right? Because at A node potential is Vx minus the drop across this region from this region to this region, and divided by resistor you get a current. So my ID will be equivalent to Vx by R2 minus 0.7 by R2 minus 0.7 by R1. Can anyone please use the calculator and get an answer for me? Vx is 6 volt. Divide it by R2. R2 is 2.3 kilo ohm minus 0.7 divided by R2. Can you please use the calculator to solve this? Anyone with the answer? Confused here, it should be kilo ohm. It's let's first try with the kilo ohm. 6 divided by 2.3. Let us say 6 divided by 2.3. Yes. 3. Zero point 0.7 divided by. Have you done this question before? Is it zero point 0.2 ohm here or just this is a, please remember that this is both are kilo ohms, right? Both are in kilos. So this will be minus 1.2. Now let me just ask you guys. Yes, yeah, around that. So is this correct? Can anyone tell me this is my diode and you have current flowing here in this direction as 1.2 milliampere. Is this correct for the diode? You have seen that
No, sir.
IS is of the order of 10 is power minus 16, right? So now our solution says the current is 1.2 milliampere. Yes, right? It is completely wrong. So our assumption, what does our assumption say? Say the diode is on. So that is clearly wrong. So what is the next assumption?
Diode is off.
Okay, diode is off. Can you tell me quickly what will be the answer? When diode is off, this is open circuit, so every current will flow through this resistor and this resistor.
It seems that R2 is a little bit higher than R1, so it seems that the most of Vx will be dropped on R2.
Yes, yes, that's correct. But
Mhm. This is
you need to find ID. This is a simple circuit,
Mhm.
so your ID will be simply equivalent to Vx divided by R1 plus R2, right?
This is ID.
Yes,
This
yes,
ID,
yes.
sir.
Yeah, yeah. Here actually, not ID. Sorry, not ID, not ID.
Mhm.
Thank you for correcting me.
Yes.
This is I2. We have because in this question we have to find I2. So I2 will be Vx divided by R1 plus R2. That is 6 volt divided by R1 is 0.2 K plus 2.3 K. So I2 will be 6 divided by 2.5 K. That is equivalent to 6 divided by 2.5. That is 2.4 milliampere, right? Anyone has any question related to this? Not, then we can move.
I have a question, please.
Yeah, yeah, go ahead.
Mhm. Mhm. In the IV characteristics of the diode, the exponential characteristic of the diode that you have previously plotted,
Mm-hmm.
uh, you have shown that yes, the the prayer slide, yes, this one. Y-
This one?
yes.
Okay.
You have shown that when voltage increase
Mm-hmm.
more than zero point 0.7, the voltage dropped on the diode should be 0.7 volt, right?
Now come again.
If if we have a circuit like the one next to the characteristics. So
Mm-hmm.
if this battery was a voltage power supply, it was a power supply of voltage source, and I am
Mm-hmm.
changing this voltage source. If I
Okay.
increase beyond zero point 0.7, if I go beyond more than or exceed zero point 0.7,
Okay.
what will be the voltage across the diode from the
Okay.
characteristics? It seems to be
Okay.
zero point 0.7.
This one? Are you talking about this
Yes,
one? No,
yes.
this is actually, I have just clearly mentioned that your diode doesn't work here, because you see that, see, this is diode. It always has a resistance in series. It's intrinsic resistance, right?
Mm,
And if you go on increasing this voltage here, they will all, for example, from this voltage to this voltage, you will see that your diode voltage is also increasing, right?
mm,
But
mm, mm,
after you reach this particular voltage here, this V cut in, the diode voltage does not increase, and
mm,
all the current is limited by this resistor, and whole potential drop will occur across this resistor, right? So
mm,
that's why whenever you operate a diode, you also connect a resistance in series, so that this is series resistance, so that you don't damage the diode. Because as I said, from the band diagram point of view, which you may study in your higher classes, this is your built-in potential, right? That gets formed because of depletion region, right?
mm,
Here. So what happens is, if you go on increasing this further, so what can happen is that there can occur a breakdown. So this characteristics, so diode may get damaged, it may get burned. So whenever you go on buying the diode, there is a specification given by company that you need to operate the device within a certain voltage range. So in that voltage range, your diode will act properly. Okay.
mm, mm,
So that's why we use a zero point 0.7 voltage fixed voltage for diode, because it gets fixed after a certain voltage. You go on increasing the voltage, the diode voltage remains at zero point 0.7 volt. Okay.
mm,
Okay.
mm.
Anything else you want to say?
No, no, no. Thank
Okay.
you.
Okay. Now, we are saying in this question, read here. This question says that you need to use a non-ideal diode. Non-ideal diode means we have to use consider, or we have to consider resistance as well. Okay. From the diode equation, you know this is Is exponential of. Let me just use only this term, Vd by Vt. If you differentiate it with I Vd, what you will get? Sorry.
Conductance.
Nice. We'll get a conductance. Please correct me if I'm wrong. Can I just write it as ID back? Is it correct? So my resistance will be reciprocal of this, right? Resistance will be dID by dVd, right? Is this correct?
Yes, sir.
Okay.
Yes, sir.
So just one more key point here to use it directly in circuits. So here you see that RD is Vt by ID, right? So if I have a diode and it has a resistor RD here. So if you don't know what is ID, can you tell me what is the potential drop across this resistor? Anyone? It will help you with a lot of questions. Can you tell me what is directly what is the voltage drop? I'm saying drop. Drop is I into R. Everything is present in the slide. You just need to look at it. What is the potential drop across the resistor? If you have a good eye, you can directly see the answer in the slide.
RD into RD.
Yes, it is ID into RD,
ID into RD.
right? It is ID into RD, yes. But can you tell me directly the value of this? What will be the value of this? Can you tell me the value? It's easy. It's written in the question itself. Read the question. You
26
will see.
millivolt.
You will see. Read the question.
26 millivolt.
Yes, it's 26 millivolts.
26 millivolt.
Yes. So if you don't know you don't know the current flow in the circuit, if you just want to know what is the potential drop across it, you can just directly, because you saw the derivation, right? From the basic equation, you can get a very clear approximation that your potential drop across the intrinsic resistance will be equivalent to 26 millivolt. And this 26 millivolt is only valid at T is equal to 300 Kelvin, that is room temperature, and it may change based on the temperature. So what does the question say? What do we need to do? Now it says that if VD changes by 2.4 millimole, what is the change in ID? Right? It is simply that we just found that dID by dVD is equivalent to, I'll join you now. It is okay, dID by dVD is equivalent to ID by VT. So can I write it as dID is equivalent to ID by VT into dVD? Is it correct? Now what does the question say? dVd or delta Vd, that is change in Vd, is given to us as 2.4 millivolt, right? So we need to find delta Id or delta Id, okay, write it as delta Id, that will be given by Id by Vt into 4 millivolt, 2.4 millivolt. So your Id is also given, right? Your Vt is given. Can you find the delta Id? Yes? Okay. Let me just okay, we have three more questions from this assignment. Let us go through quickly. So what will be the KCL? Please help me with the KVL, sorry. Help me with the KVL from top to bottom. So first let us see the question. What does the question say? We need to find I1. What is the current I1? I1 is here for the diode. And I will just denote it as X and I will denote it as Y. What will be your approach? Have you done this question? Anyone tried this question? Yeah, please.
Uh, Excuse me, can you hear me?
Yeah, please.
This question is actually like terribly tricky because the voltage drop across the two diodes is not the same, and it goes into a like into a system of two variable two unknowns with all of them involving exponential. So
Why
how do
is
you
it
solve?
why is it not same?
See, VD1 and VD2 will be different, right?
Why?
Because the currents flowing through them are different, right? Because uh,
No. When you okay, so in all the diode questions, the
because
potential.
most of the questions have this problem that like if you use the diode equation and the load line, the answers don't match at all. And if you use that
No,
0.65 approximation, like then it goes haywire. Like you plug in back the equation and like
Oh,
the IDs don't match.
so actually in circuit analysis is uh, that's why that if you go on using the diode equations for all the diodes, it will have to do the numerical solution. But to make your life easy, you know that diode in circuit analysis, if you use piecewise linear model, you have to use it as V naught minus V cut in by some resistance, right? So this is your current. So this is your model for diode. So for those both diodes, if it was given you separately that they are not identical, we can have different potential. But in your circuit analysis, you have to model it using this some cut-in voltage plus some series resistance. So here you don't use the series resistance as well. You use just by using the cut-in voltage, and here you can assume it as 0.6, 0.65. Usually in all the set of questions you have to use the 0.65 assumption. So you start with that assumption in this question, so that will help you solve the question actually.
Then it becomes actually trivial, like because even in the last couple of questions, right? Like it's like it becomes like unmanageable if if you just use they should mention it somewhere that okay, use the linear
Okay,
model or this model or that
okay.
model. And
Just okay. So try to do one thing. If it's not given, do you have the options where there is a range given? What is the answer range? Is that given?
the options are given, but the thing
No,
is
no,
that
not options. I'm saying, is there a particular range given for a particular answer? Like, for example, if this is the answer 2, you get a value of 2. So, is there a range given? The answer should be between 1.8 and 1.2.3 or something like that.
sometimes they mention 2 digits of accuracy and those sort of things.
Okay. So actually, in diode questions, in circuit analysis, you have to assume it with, for example, in this question, you don't have any other way. You have to assume it with this model where you assume it with some voltage, that is a current voltage, and that's a good approximation. So you don't need to worry about it. And let's see if I will assume it with two same potentials. See if I can solve this, and maybe it will help you. Okay. So let's go a simplified version. I will just substitute it with simple cut-in voltage that is of 6.65 volt. So I can directly replace. Okay, so you can follow a book even. You have Millman. You have. I won't recommend that book, but from a beginner's point of view, you can use Godse Bakshi as well. So they have a lot of questions given. You can try some for your understanding. You can try those questions as well, and you will see that in circuit analysis, you will see that you have to replace by using this piecewise linear model. Okay.
Sir, how to know whether we have to use RD or not?
Actually, if the assignments who have made these assignments, they have not clearly mentioned it, but they should clearly mention them because for ideal diode, you don't use ID, but in the real world, in non-ideal applications, you have to use RD. So I cannot say about the questions when to use and when not to use. But I would prefer if they mention it in the questions that this diode, for example, in this question, in the previous question, it was given, where was it? Here. Like in this question, it was given, can you see the question? It was given as a non-ideal diode. Here you can, if this diode is given in analysis, you have to use RD. But if you don't get an answer for some questions, you can then use this RD as well because diode has an intrinsic resistance with it. Okay. So let's see from the KVL point of view, you see that this is your VCC. This will be a potential drop of 0.65. This will be a potential drop of 0.65. This is R1. This is R2. Okay, this is X node. This is Y node. This is X node. So now, do you know that what will be the potential across this R1? The R1 will be 0.65 volt as well. So if I use the KVL from top to bottom, KVL, so it will be VCC, then voltage drop of 0.65, then a voltage drop of 0.65, and then Vy, that will be equivalent to 0. VCC is given to us as 4.6 volt minus 5, 13, is equivalent to Vy. So this is a potential of, is this correct? Please, have I done it correctly? Okay, so now can I just write Iy here? What will be the Iy? This is Iy. Iy will be potential Vy by R2, right? We got as 3.3 volt. You have to, whenever you assume, you have to check with the answers as well. You can use 0.65, 0.6, 0.7, and don't go beyond 0.7. Okay. R2 is given to us as 1.2 kilo. If I just calculate it, this is 3.3 divided by 132. It gives me a value of 2.75 milliampere. Okay. So here you can see that this is a current of 2.75 milliampere. So what we need to find is I1. What will be the current from I1 diode? So can you help? Can anyone tell me what will I do? You have here diode here, you have resistor here, you have another resistor here. Now you want to find this current. Let's say I1. Let's say this is I2. And it's I total. I total you know now. It's 2.75 milliampere. Can you tell me how can I find I1 now?
IT minus I2. I equal
That
to
is at Y I will do KCL. That will be I1 plus I2 will be equivalent to 2.75 milliampere, right? Now, can you tell me what will
yes.
be can you tell me what will be I2? I2 will be simply potential across R1 divided by resistance of R1. And can you tell me what will be the potential across R1?
0.65.
I have assumed 0.65, so it will be 0.65 divided by yes R1. R1 is 5.1 kilo. Okay,
I want
0.65
to ask
divided.
a question, please.
1 second. 5.1 kilo. That gives me a value of 0.127 milliampere. Now you know I1 will be equivalent to 2.75 milliampere minus 0.1%. Can just okay, please go ahead.
What if in this question we
Mhm.
will assume that it is required to answer this question same as the first one where we have used the iterative method? How we are going to do it with this question?
Okay, you want to find it with the iterative method, yes? You can do
Yes.
it. Okay, you can do it. You want to find, but they have not specific. Whenever they have not specifically given the iteration, you don't need to use it. Okay,
Yes, I want to
because
assume, I want to understand how to solve such a question
okay.
if it is
So
required to.
yes. So in any question, whenever it's not given the given that you need to find the iteration, you don't need to use it. But for your satisfaction, for your clarity, whether you have got the right answers or not, you can use it, and you will get the right answer with that as well. So for example, here you can use the iteration method, and but you have two diodes here, So that won't either matter, but that will complicate your answers. But if you have options given and it's not mentioned that you need to find the iterative method, then you don't need to use it. And you have seen that from the assignment point of view, they should have mentioned that use the curtain voltage of 0.65 whenever it's not given. They have not said so, but at the larger point of view, if you see in the books or somewhere else, you will get a clear directions that what to use and what not to use. Okay.
I think, please, sir, I want to understand something here in this question.
Okay.
Because the question is saying that assume that the diode is following the standard diode equation.
Mhm.
And what is meant by standard diode equation? If he is giving IS, I can deduce
Yes, yes,
that
yes.
he is
Yes, you can
referring
you
to the
you can
exponential
you
model.
can you can use iteration as well, but from the assumption here and from the solutions from the options you have, this is my first iteration, right? This is my first iteration, and you can see from the if you solve this question, if you get your it from the first option only, so then you don't need to go to another iteration. In the for example in your first question as well, while you use the standard diode equations and use the iterations, you first directly used this method, right? I naught is equal to v naught minus vt by r, right?
Yes.
Directly, you directly use this, then you start iterating. But
Mm-hmm.
if you get an answer directly from this equation, you don't need to go to the iteration method. Okay, so
Mm-hmm.
that means that your first guess was absolutely correct.
Mm-hmm. So what you are going to do if it is requiring the iterative method, you are
Yes,
going to use the
yes,
same equation.
yes, yes, yes,
Uh,
yes, yes.
and then you are going to have three equation you are
I can I
substituting
can
in it.
I can say that since these diodes are identical, and I can say that from let's say X node here, the same current will flow. For example, this I1, and I can use this for only single diode. The whatever true is for this diode will be true for this diode as well. So you don't need to worry about it. For example, if I use them only this circuit, whatever true is
Mm.
for this diode, that will be true for other diode as well. Because from the iteration, you will have to find this diode voltage, that is a current voltage. That is clearly a material property. So since the diodes, wherever you do this in here in these assignments, these diodes will be identical. Whatever VD you will find for this diode will be for other diode as well. So you don't need to use the three equations. Okay.
Mm, mm.
Try to make as simplified as possible your solutions.
But Sankran has said, I think at this point, what he have said is logical. I
Yeah, yeah,
understand what you said, but he
yeah,
said that the
absolutely, absolutely.
branching.
Yeah,
Mhm.
absolutely. Yeah,
So
whatever
we
is
cannot say that they will be identical because
no,
the
no, no, no,
moving
no, no,
current is different.
no. Identical by identical, you mean that your IV characteristics will always be identical. There will be no difference in that. You
Yes,
understand
sir.
that?
We understand this. We
Yeah, yeah,
understand this.
yeah, yeah. So that will be identical. For example, if this diode is on, this diode is on, both will have a same potential drop. So that will be same unless it's given. Potential drop will be same. Okay. So if it's given D1 and D2 are not identical, then potential drop will be can be different. For example, if one is D1 is silicon diode and D2 is germanium diode, right? Then this has the potential, let's say 0.65, this will have a 0.3435. So then you can say they have a different potential. But if diodes are similar, their current voltage will be similar. So that won't be a difference.
But from again, please, from the exponential relation, if you are saying that the same current is passing through the two diodes, this means
Mm.
that the same voltage is dropped, right? And if you mean
Yes.
that the same voltage is dropped, you mean that R1 is infinite.
No. R1. Why is R1 infinite?
How, sir? How they are not in series.
No, no, no. Please come again. Can you please?
When you are saying that the same current will
Mm-hmm.
the same voltage will be dropped on the two diodes because they
Mm-hmm.
are identical, so
Mm-hmm.
you are assuming that you are going to have the same current. And when you are assuming that they are going to have the same current passing through D1 and D2, so you are assuming that R1 is infinite.
Okay, by that logic, okay. Okay, look, this is your diode.
And this is not the case in the question because R1 is not infinite.
Yeah, 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 you're absolutely right. So,
And this is, I think, what I deduced from Sankaran. Am I right, Sankaran? Sankaran, I am right?
Yes, yes, it's you're absolutely right, and the same goes for many most of the questions. But
mhm.
yeah, now since this is just a one mark assignment, and probably that we have overthought, we can use the simple model.
Wait a second, wait a second. Let me just understand your point. It's a very valid point. Okay. hmm Okay. Just one thing. When I said this is a this is a curve, right? This is I, this is V, this is your cut-in voltage, right? So for diode, when you see a diode conducting, I said that it will act as a simple constant bias. No matter how much voltage you increase across it, the potential will remain same, right? Because if you go on increasing the bias, this goes like this. This particular, even the whatever the current value is, you see here, whatever the current value is, this VD remains fixed. Okay, so let's assume here the okay, this is a basic diode property. Let's assume even if there is a current of let's say 4 ampere here, okay, let's say 4 ampere current falls here, and let's say here it's a 2 ampere and 2 ampere falls here. From the physical characteristics of diode, they still will have a same potential drop after we cut in. What if the current was here in the off state, let's say when the low current was flowing, then you can say that, for example, in this location, then you can say that the current and diode potentials, that is VD, can follow the relation. The way you said that if diode 1 has a current of let's say 1 milliampere, diode 2 has a 2 milliampere, they may have different potentials because you have not reached this cut-in voltage. But from the physical point of view, even though you go on increasing the applied bias, you go on increasing the current exponentially, that cut-in voltage will still remain the same for the both diodes. Even if it is a 4 ampere, 8 ampere, 10 ampere, even if though it is a 4 ampere. So that is not a case with the diodes in when you operate them above the cut-in voltage. So that doesn't make your resistor R1 infinite. Okay, because when, as I said earlier as well, this because we are here using the ideal address VD, after a particular voltage, no matter how much current flows, this VD remains constant. Okay, hello.
Yes, I got your point, sir. I got your point.
I
But
think you're still not understand this concept, I guess. But
no, no, no. I got your point. I understand what you are saying, but what you are saying also, you are making some approximation in this curve. You have did an approximation, by the way, but it is acceptable approximation. But this is, I think, there is an approximation.
Oh, approximation, you can use the approximate model, but from the physical point of view, if you see the
Mm-hmm.
diode operation, after the diode is on, the potential across the diode, I'm just saying that across the diode remains fixed. It doesn't change, because if it does not remain fixed, then you will go on increasing the applied voltage. Your current should increase exponentially, but you won't see that in the diodes, because diodes then get burned out. So there's a particular
Mm.
limit. So after a particular voltage, that's why if you buy the diode, you see the physical specification of the diode, you will say that it has a particular constant voltage or particular cut-in voltage. That's why you will see the questions as well. And the linear model as well, it's all based on the same concept. Yeah, approximations are there. That is true. But I
Mm.
guess
Mm.
these are the valid approximations. I
Yes,
hope.
yes, yes. I got
Okay.
the point. I got it.
Okay.
I got it.
Okay.
Thank you.
Okay. I guess I should show this question first, because this needs so have you guys done transforms like Laplace transform? Have you studied any maths? You may have opted for this subject, math subject as well.
Yes, sir. In signal and system.
Yeah.
Yes, sir.
So okay, so I will just say that in this question you have to use these Laplace transform. From my point of view, I will use Laplace transform to solve this question. You may have seen for the capacitor how, do you know what is how you transform this capacitor from time domain to frequency domain? I hope you know that. So let me just say that in this question, what we have to do is that we have to find the amplitude of the ripple voltage. That is simple. We have AC input voltage. We have AC input voltage. Okay. We need to find here V out here. We need to find V output AC. Okay. We need to find its amplitude. That is a magnitude. Okay. So if I just when you do the AC analysis, you just ignore the DC points. I will just make a circuit with only AC signal. And this is a continuation of the earlier question. Here, it's given that this diode, for if you do the assignment, please make sure that for this diode, make it as a uh, what I can say, real diode, non-ideal diode. This is R. This is your C. Can you tell me what for the capacitor? What is the Laplace transform? Anyone?
1/SC.
1 by SC, right? So if I
Yes, sir.
Yes,
okay,
sir.
so we have here AC signal as the input. I will just write it as input. We have for the AC, always whenever the AC is given, you have to use the incremental resistors for it. Even for the MOSFETs as well, we will study in maybe in next week. So this is RD here, this is R, and this is, sorry, this is here 1 by SC. So these are in parallel here, right? I will just denote it as R1. I will just denote it as R. My R will be equivalent to R1 into 1 by SC divided by R1 plus 1 by SC. Is it right? So that will be equivalent to 1 plus R1 SC, correct? And that will be in series with RD. So my R total will be RD plus R1 divided by 1 plus R1 SC. But what we have to find is that we have to find the output voltage across this capacitor. So we need only find here V output, that will be simply equal to R with this R divided by R plus RD, that is my R total, right? Multiply by V input. But we have to find the magnitude. You know that magnitude of A plus iota B is equivalent to under root of A square plus B square, right?
Whole square plus
Okay, so this is R V input divided by what is R plus RD? That is RD plus R1 divided by 1 plus R1. Let's see. So what you need to do is that you need to check, you have to find this denominator, and then you just need to do the magnitude of this and you will get the answer. And this is for your assignment. So if you have any questions till now, I can just repeat it, but I'm not putting in the values because we have to submit this as an assignment, I guess. I have done actually one mistake. I should not have shown this assignment. I have to show the different assignment, but it's okay. I'm not giving you the values. So can you tell me if you have doubt in this question? No. It's very easy. You just have to find this resistance. You just find the V output, that is simple resistor divider. R1 plus, if you have to find a voltage across this. And then for S, you replace S by J omega, and that will give you omega square in magnitude. Okay, so if you don't have any questions on this, I can move to this last question. That is on photodiode. So can anyone tell me what is a photodiode? Anyone? Okay, so first thing in the photodiode is that you shine the light, you get the current. Okay, so do you use the photodiode in forward bias or reverse bias? Do you want me to give an explanation on photodiode in the next section? The basics of the photodiode, because if we are doing this, we will do the directly question, or I will just give you a brief discussion of what is photodiode, how it is operated. Okay. From the question, let me just put here it is using the reverse bias or zero bias. From the question point of view, what you have to do is that you have to find what is VL by V naught. Okay, what is VL by V naught? So the resistance to equal such that the maximum power. So you have a keyword here, maximum power. You know, if you have any function f of x, if you have any function polynomial or something, let's say a plus b, x plus c, x, k, or whatever. So how you find the maximum? You differentiate it with respect to x, right? And then substitute it with 0. And then you get the some values for the x where it is maximum, right? Is it how you do it? So similarly, in this question as well, what you have to find is you find the power across the load. That will be simply VL multiplied by IL. Okay. So here it is I diode, it is IL, and you need to find what is IL. From the simple KCL at X node, at X you will find that I naught is equivalent to I diode plus IL, right? So your IL will be simply equivalent to I naught minus I diode. Now you know what is I diode? Is exponential of VL by VT minus 1, and then you can write it as PL is equivalent to VL I naught minus Is exponential of VL minus VT minus 1. So as I said, To find the maximum power here, we differentiate and substitute it to 0. Here as well, we differentiate it with respect to VL and substitute it to 0. You can do it. You have this assignment submit. You can do it, and I will just give the answer. You will find that VL by VT equivalent to. After you do this differentiation, it's an easy differentiation. Substitute to 0. Find a value of VL by VT, and it will come out to be 22.05. Okay, and the equation you will see after using this substitution, you will get VO by VT is equivalent to VL by VT plus log of 1 plus VL by VT. I have given the whole solution because now you can just directly substitute VL by VT in this equation and you will find V out by VT. Then you just need to do VL by V out to get the answer. Well, please try to do this. This is from from the maths point of view. You just need to differentiate and substitute to 0. And I will give a brief introduction to photodiode in the next session. Even if you have any doubts in the next session, you can ask again about the diodes. I guess next session will be on the MOS transistors, that's MOSFETs. And we can discuss it. Yeah, please.
Sir, how to get this PDF?
We as a team, we share this to the NPTEL team. They will share with you. You will get the access to the folder where you will find the YouTube link and the PPT as well from the yesterday's session. I guess the session was yesterday from the first TA and from my session as well. Yeah, Sankar, please.
Yeah, so this problem is also like it's lot of things are varying. Like RL is varying, and IL and ID is also varying. And
okay, ID is substituted by.
This B mode is dependent on ID.
What is
and it again comes out into like this. You cannot even by simplifying, you cannot avoid two unknowns.
What is
there are
that?
two separate equations, and we have to maximize for a third equation.
I think.
How you got do you have a detailed working of this, or
in this equation you're talking about? I have notified as A.
This has got around 2 or 3 unknowns. See,
what is unknown?
And ID is unknown. Everything is unknown.
Okay, so PL is a variable. Okay, it depends on VL, I naught, IS, and VL again. Yes. Now look here, VT is constant. Do you agree? Yes. IS is constant.
Yes.
And I naught is also constant here.
I naught is the current through the diode?
No. I naught is here. You can see here. I naught is this.
Okay, I naught is constant. Okay.
Okay. Now you are left with only VL. PL is dependent on VL. You have now just one dependent variable and independent variable.
See, VL is equal to VD, right? Because
VL. Okay. No, VL is not equal to VD. Yeah, you can say that VL is VD. It's one and the same thing. You can just write here VD. It's no issue. You can write here VD.
Okay. But the thing is that the moment you change, see, the question is saying that you have to change the RL, right? So at the
Actually, what is they have given that you don't. If the question was you have to find RL, then you will get that RL from this equation. If there would have been another condition given to you as well, but here in this question you don't need to find the RL. But from this equation, from this PL, you differentiate this VL, you will get for a particular condition of VL, you will get a maximum power. But what is VL? VL is again IL RL. Then you will get a condition for RL. But in this question, you don't have to do that. You just need a condition for V naught. Okay, so actually they have written as add this resistor value with the voltage across the resistor coming through this VL and RL. They have given that these are the variables, and you just need to find VL by V.
Okay, thanks.
Okay, thank you. If you have any questions still left, you can just discuss this in the next session. You have to submit the assignment, so that's why avoided putting the values for most of the questions because I somehow did something wrong and I used the assignment that is more or similar to the assignment that you have to submit. But it's okay. From the next week, maybe there will be the questions with a slight different values, so we can solve them fully. If you guys don't have any other further questions, we can just end the sessions, and I will see you next week.
Yes. Mm-hmm. Plus, please, Muhammad, can you please make sure that the TAs that are the actual TAs of the course are going to post these materials, because they are really the TAs of the course, but I am not able to see them in anything.
Okay,
No
actually,
question
this.
they are answering, nothing they are doing.
Oh no, why? But for what I'm not doing, I'm not getting it actually. So,
Mm-hmm.
so you're not getting what?
They are not answering any question. We cannot see them, and the previous session of
Okay,
yesterday also, no materials, no links are
okay,
provided.
okay. So maybe they are waiting for you to submit the assignments first. I think I don't know. They will share. They should share a folder with you. And they will share the Google
Please,
Drive
if you
link
have
with.
a contact with them, please contact them, please.
Okay, okay. I will try to email the NPTEL head who is handling this. I will tell her to share with you the links of the drives folders. But if you want, I can just paste.
If you can do it directly with us, it will be great.
No, I cannot directly, but that is not and what supposed to do. Then you will get a YouTube link for that. You don't have to worry about this. You will get a folder link where you find the uh, YouTube video as well as you will find the slides as well. I
Okay.
will just I will
Thank
just email them to share this. You don't have to worry about it.
thank you so much. Thank you.
Okay. Okay. See you guys next week. Bye.
Just see you. Goodbye. Have a great day.
Okay,
Bye.
sir.
You
Thank
too.
you, sir.
Okay. Bye, guys.
Thank you, sir.